All right, so this video is on biological nucleophilic substitution, so as well as a couple other things, but it's really just showing you the practical applications. So we have phosphates, we have diphosphates, we got triphosphates, right? We've seen these in our biology class probably, abbreviated PII, meaning like an inorganic phosphate group. We can also have it abbreviated as like an monophosphate, where we have it like an ROP group, and that would be where R is the alkyl group. Okay, we can do the same thing with diphosphate and triphosphate groups. And then we can see that in adenosine triphosphate, which is our body's source of energy, right? Gives you wings. At least it gives Tyrone Bigham some wings. And then we also have a cool example here. That's S-adenosyl methionine, abbreviated as SAM. We have this sulfur group with the methyl on it. That's a sulfur with a positive charge on it, so it's a sulfonium ion. And this serves as it's basically like a methyl iodide, for example, like a methyl alkyl halide. And that methyl group is susceptible to nucleophilic attack, and the SR2 positive is abbreviation for like the rest of that giant molecule. And that's a good leaving group because it's positively charged, and then once it leaves, it's neutral. So nucleophile can come up, attack that methyl group, and essentially methylate whatever that nucleophile is, and this actually naturally occurs in the body. Really cool process because it's nucleophilic substitution in your body, right? You thought this was just in a beaker or a round bottom flask, but no. Let's see a real example of it. So we've got norepinephrine, and that can get converted to epinephrine using SAM. Okay, so in this case we have, let me get this organized. In this case, we have a lone pair on the nitrogen, which is a nucleophile. We also have an oxygen on here, which is also a nucleophile, but that nitrogen is more basic, and remember, basicity and nucleophilicity parallel one another, and so that nitrogen is more nucleophilic, and so that's the nucleophile that attacks that methyl group, kicks off that SR2 plus, and then after the loss of a proton, that's what that minus H plus means, we get an amine, but now with a methyl group on it. So, and that's how that's the process of converting norepinephrine to epinephrine. Fancy, right? It's pretty cool. Oh yeah, these are neurotransmitters. Epinephrine is actually adrenaline. Norepinephrine, I think, is also called like noradrenaline. Basically, they stimulate that fight or flight response in your body. So super cool process. Substitution reaction. Boom. OCAM or bust, right? Organic synthesis. So organic synthesis is the systematic preparation of a compound starting from basically basic materials, starting materials, and you can create these compounds in one or more steps. Okay, so let's see, readily available starting material by one or more steps. Okay, so more steps would be also called a multi-step synthesis, is probably one of my favorite things in organic chemistry. I guess my most favorite thing would actually be retrosynthetic analysis, which is like working backwards from a product. So let's say we have this alcohol here, and we want to figure out how to make it. So that's the idea of synthesis, right? We're making something in one or more steps. And from what we know now, we're starting to build our toolbox. We have two types of substitution reactions. We have an alkyl halide plus a nucleophile gives us a new product, right? And so what alkyl halide can we draw and with what nucleophile to get this alcohol? You can really just draw any leaving group here. And that weird arrow, it's almost like an equal sign with like a caret or like an arrow. It's a retrosynthetic arrow, and that's basically just saying, hey, what did this come from? this alcohol working backwards to an alkyl halide, alkyl bromide specifically, plus a strong nucleophile because it is a primary alkyl halide, and that would give us our alcohol. And there you have it. That's pretty much organic synthesis in a nutshell. Obviously, we only have one type of reaction thus far, but we will definitely build on that, and our toolbox will get huge, and then we'll be able to build pretty much I don't want to say anything, but we'll get pretty fancy. Okay, so let's say we've got this ether here. We got a methyl on one side and ethyl on the other. So working our way backwards with substitution reactions, we can kind of make this in two different ways. We can kind of break that into a red and blue section, working with an alkyl halide and a nucleophile, of course. All right, so let's just split it up into red and blue. Our first, maybe alkyl halide could be methyl iodide, okay? And then the blue part has to have an ethyl. And so let's say we have an iodine as our leaving group again, and then we got an ethyl there, okay? That would work. Now, what would the nucleophile be in each of these cases? Well, for the blue nucleophile, what we would have is we need an oxygen. So we just throw an oxygen on that methyl group hanging off on the left. So we got a methoxide. Same thing for the other side, but it's an ethoxide to bring in that CH2CH3 group. And jam those two together, and we got the product. Jam those two together, and we've got a product. So we'll learn a little bit more about this type of synthesis, but there you have it. We got the skills to pay the bills and make weird stuff. So that's pretty much substitution reactions in a nutshell. Practice them a lot. You're going to need it.